Hey everyone, welcome back. I'm going to be covering another chemistry-based passage today called Purification of Caffeine. And just scrolling through it, this one has a lot of experimental considerations and graphs, so I think it'll be a good case to cover. So the passage states, caffeine is the most valued for its ability to temporarily ward off drowsiness and restore alertness. It belongs to a class of large class of compounds known as alkaloids, compounds that contain only basic nitrogen atoms. These are of plant origin and can be extracted from tea bags, for example, through a series of purification steps. Now, there was nothing really of value here in terms of information or what could be kind of pertinent to questions. At least that's my assumption here. So I'm not going to fixate on this part too much. And then they give you a little diagram of the caffeine molecule. I'm assuming this is going to be pretty vitally important. So the extraction purification, it states, after brewing tea bags in water, the liquid extract is filtered to remove any insoluble material. So that's pretty important, so I'm just going to underline that. Then it states, the remaining supernatant, which is the top layer, can then be separated through liquid extraction. The two solvents used in this extraction step are water and dichloromethane, or DCM. So, again, the core pieces of information here are the liquid extract is filtered to remove any insoluble materials, and that we use liquid extraction using water and dichloromethane. The two solutions then separate into two layers, a brown aqueous solution and an organic layer with dichloromethane. Evaporation of the organic solvent yields a caffeine compound with impurities such as green chlorophyll. So you have to kind of read between the lines here, but what they're stating is when you evaporate the organic solvent, you're left with the caffeine compound with some impurities. This kind of indicates that the organic layer in question here, so the layer with dichloromethane, is the one filled with impurities to begin with, because that's what we're trying to evaporate and get rid of. The next step in this purification process states, to further purify the caffeine compound is possible to do through sublimation if the impurities are non-volatile. Crude material is placed at the bottom of the sublimation chamber below a cool surface test tube. Impure caffeine is extracted and then heated to sublimation. A vacuum is applied to the airtight environment by sucking all of the air out of the chamber through the vacuum/gas lines shown in figure 2. Now, I know there was a lot to take in there, but it looks like they gave us a series of steps. So I think everything we read here will be more or less summarized with this. So it says cool water goes into the test tube. Where's 1? So cool water is put in here. And then it leaves here. Number 3 is vacuum/gas lines are creates a near zero pressure environment. It constantly removes gas as it is exposed to from the system. So from this part of the tube, gas is going to be continuously sucked out to ensure that there's a stable vacuum that's built up within the chamber. Crude caffeine material is placed inside the base of the sublimation apparatus. So the crude material we're just going to place down here. Solid, non-volatile impurities are left at the base of the apparatus after sublimation. So as you can see from the other diagram, whatever impurities are or what we're trying to get rid of will be just left alone at the bottom here, and our solid crystals will form around here. Now I'll summarize this again in just a second. And then it states that external heating drives the sublimation process. The gaseous caffeine will separate from the less volatile impurities and form crystal caffeine deposits along the cool surface. The caffeine deposits are then collected for the next step in processing. So just to kind of give you a visualization of what's happening is, when you have the impure caffeine, after you do your liquid extraction, which was outlined here, you can take that crude product, put it towards the bottom of this chamber, then you heat up the bottom of this chamber, and what's going to happen is the caffeine product that you're trying to actively purify will evaporate, and as the gaseous caffeine evaporates, it will eventually meet this cooling tube that's up here. When it comes into contact with the cooling tube, the gas will quickly turn back into a solid over here, so where they showed the purple. Solid crystals will form around the cooling tube to purify the caffeine from your crude solution. So to kind of give a quick summary, you're undergoing sublimation here. So you're going solid to gas, and then here you're undergoing deposition, the opposite process, where you go gas to solid. And usually what they specified is this will primarily work if the impurities you have present are non-volatile. So in this case, the impurities are not evaporated with the caffeine. So moving on, it says the vacuum is the key to the process of sublimation. For a substance to change phase into a gas, its molecules must reach a vapor pressure equal to that of the external air pressure. Because the vacuum lowers the air pressure, the caffeine can reach the vapor pressure at lower temperatures and bypass the liquid phase. So that's another important point here. We're trying to bypass the liquid phase. Again, to kind of refer back to the example, what they're saying is this tube that's actively working to create the vacuum in the system is going to make it so caffeine is able to go from a solid to gas directly. In the absence of this chamber, where a vacuum is being created, you might have to heat up your solid a lot more in order for it to turn into a gaseous state. And even in that case, it might have to turn into a liquid first. And then it shows the caffeine phase diagram with the arrow indicating the path of the caffeine sublimation. So you can see here it goes straight from solid to gas. At no point does it cross to the liquid phase. So the first question states, how would the caffeine sublimation phase diagram be affected if the vacuum in the apparatus is allowed more air pressure into the chamber? Well, remember, the purpose of the vacuum apparatus was to create a zero pressure environment. And what that will allow you to do is, like it mentions here, for substances to change phase to a gas, its molecules must reach a vapor pressure equal to that of the external air pressure. So we need it to be a low pressure environment such that we can convert the compound straight from a solid to a gas. Now, in a case where you're increasing the pressure, well, look at the axes on your arrow. Pressure is the y-axis. So if you essentially increase pressure, this arrow would have to move up. So it would be somewhere around there. In which case, sublimation might not even occur. It might actually have to go to solid to liquid to gas. So we look at our diagrams here. Well, the first one points an arrow upward, but that would indicate a change in temperature. So this is not what we're looking for. Okay, why is that highlighted? Okay, so just ignore that. The second one shows the arrow pointing down. Now again, these two don't really take into account what it is we're mentioning. We're talking about the same arrow. We're talking about the same direction. We're just increasing the pressure that was associated with this specific system. So looking at these two diagrams, C and D, we can see that in this one the arrow's been moved up, and in this one the arrow's been moved down. Now the question stated that, like I mentioned, more air pressure into the chamber. If there's more pressure, then the arrow should move up to region of more pressure. So the correct answer here would be C. The first question says, which of the following types of hybridization describes carbon atoms of the caffeine molecule? Well, we can scroll up to the caffeine molecule. So let's just circle all the carbon atoms we have present here. So there's a carbon there, carbon there, carbon here, 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 and here. Now, if we look at the carbon atoms that are embedded within the ring, we see that this one is sp2. Let me switch colors here. sp2. This one is also sp2. And this one is also sp2. So remember, when a carbon atom has a double bond somewhere in one of the 4 bonds, the carbon atom is considered to be sp2 hybridized. So in this case, the carbon is double bonded to the oxygen. In this case, it's also double bonded to the oxygen. In this case, it's double bonded to the nitrogen. So in all these cases, all these are sp2 carbons. But if we look at these side chain carbons, all of these are sp3 hybridized because they all have single bonds. sp3, sp. So we can see that our caffeine molecule has a blend of sp2 and sp3 hybridized carbons. So let's go down. So sp2 is option 2 and sp3 is option 3. And that would be A, which has 2 and 3. So this question asks, why was dichloromethane, CH2Cl2, used in the above extraction? So what was the purpose of using the dichloromethane here? And just referring back to when they spoke about the dichloromethane, they said it was used in the initial extraction phase along with water. So the options that they said here is it has a binding affinity with water. Well, CH2Cl2, which looks like this, is more or less a pretty non-polar molecule. So in an instance like this, it really shouldn't be bonding with water. As you guys may know, water is highly polar. It's one of the most polar compounds. So in this case, it becomes very unlikely that these two would really get along, given that this one is non-polar or maybe very slightly polar, and this one is extremely polar. So polar, non-polar. So no, it shouldn't have a binding affinity with water. It is immiscible with water. Well, that should be true. Dichloromethane should not be able to blend with water. And again, they kind of do refer to that in the question stem here, where they say this extraction phase results in 2 layers, a brown aqueous layer and an organic layer with dichloromethane. Well, we can assume that the aqueous layer was because of water, and the organic layer, as they stated, was the dichloromethane. So option B is correct. Option C says it is immiscible with caffeine. Now, that might be a difficult call to make here, whether or not it will be immiscible with caffeine, because that would involve you kind of gauging this caffeine molecule and whether it's polar or non-polar. But with the options that we have here, B we know is correct, and option D says it has a binding affinity with caffeine. Well, that shouldn't be the case, because remember, we use the DCM, or the dichloromethane, to extract out all the impurities such that caffeine was left over. So in essence, caffeine was non-reactive to the dichloromethane. So in this case, D is also incorrect. So option B is the most logical choice. If the sublimation purification were to be performed with the cool surface tube situated higher than the original setup as shown on the left of figure 2, how would the results be affected? Well, they're saying the cooling tube, which is this tube that you see, instead of being placed here, if it was placed somewhere higher, let's say it started here, and this is going to be an awful drawing, and I apologize. So if that's kind of what the cooling tube looked like, if it was moved up slightly, how would this affect the process that they've outlined here? Well, remember, the crude caffeine mixture is placed at the base here, and caffeine needs to evaporate and eventually touch the cooling tube to solidify back and form the caffeine crystals. Now, if it's moved up past this pipe, which, like we mentioned, is responsible for creating the vacuum that'll allow the caffeine to evaporate at a low temperature. If that is the case, caffeine is going to evaporate slowly, and maybe a lot of the gas is actually going to exit through here because we've moved the cooling tube up. So let's look at our examples. The sublimation arrow in the phase diagram would move to the right due to the warmer temperatures experienced by the gaseous caffeine. Well, again, the question doesn't really hint or speak about changes in temperature. Rather, they're just talking about moving the cooling tube higher. So they're not talking about how hot the external heating source would be. So this doesn't really relate to the question at hand. Option B says there will be less yield as much of the gaseous caffeine will exit the sublimation chamber without making contact with the cool surface. So this is what I kind of spoke about, where the evaporated caffeine might exit through this chamber. I'll just draw it here. So the evaporated caffeine might exit through here if the tube is moved higher, which would result in a lower yield, because instead of all the caffeine reaching the cooling tube, some might escape, and then the remainder might come into contact with the cooling tube. So option B sounds correct. Option C states there would be more yield as gaseous caffeine will take more time to reach ambient temperature before reaching the cool surface where it is crystallized. I know this may seem like an appealing choice because you may think that the amount of time it takes for the caffeine to rise, it will essentially be cooler, and then it's more likely to turn into a solid. But remember, what we need here is a drastic change in temperature. So we need the cooling tube to be close, because what we want to have happen is we want it to turn straight from a gas to solid crystal form. If we move the tube higher, then as the vapors rise and they cool, they might even, let's say, form liquid and fall back down as they turn from gas to liquid, which would just defeat the purpose of what we're trying to do here. So even in this case, it doesn't really make sense what they're asking, is because we want that rapid change in temperature given by the cooling chamber. And option D states the sublimation arrow in the phase diagram would move to the left to the cooler temperatures experienced by gaseous caffeine. Now, again, you have to understand that this is kind of a red herring. They're basically just trying to throw you off with logistics of different aspects of the question. So the sublimation arrow in the phase diagram would move to the left due to cooler temperatures. So they're talking about this arrow moving further to the left, so like over here. But remember that would indicate that there's a change in temperature. So if you look at your axes here, this axis speaks about temperature. So if your arrow were to move to the left, then all of a sudden, yes, it does become harder for it to turn into a gas. But at the same time, nothing in this question stem indicates a change in temperature. They're more just speaking to the changing of the positioning of the cooling chamber itself. And the most likely outcome of that is that the gaseous vapors will escape. So I think we should stick with option B here. Okay. And the last question states, despite heating the apparatus, the scientists detect no temperature change for a short period of time during the sublimation step. Which of the following explains this observation? So if you guys kind of refer back to your thermodynamics unit, we learned that when energy is inputted into a system, one of two things can happen. So this diagram may seem familiar to a lot of you. So change in energy, and we'll just call this temperature. So degrees Celsius or temperature. So as we input energy into a system, what happens is we see this change in temperature. But when there's a change in state, such as these flat periods of the graph, when we see a change in state, the temperature actually remains constant. So if this were ice, if this was ice and we heated up ice to 0 degrees Celsius, it would stay at 0 degrees Celsius while you put in more energy until it had turned from a solid to a liquid. And then the temperature would start raising again until you hit 100 degrees Celsius, from when it would go from liquid to gas, and then it would continue to heat up. So remember, when we have these changes in state, we actually don't see any change to the overall temperature of the system. So the options we have here are: the energy added was stored as chemical potential energy. Again, this kind of, it's presenting an option that may seem plausible because yes, a part of the energy might be stored as chemical potential energy, but that doesn't explain the observation as to why we see no temperature changes. And remember, during the heating phase, they specified that it's the sublimation step. So remember, like I stated here, during changes of phase, there's no change in temperature. Now, during sublimation, something is going from a solid to a gas, which is a change in state. So again, during this phase, there would be no change in temperature. So A is not correct. Option B states the energy added had a negligible effect on temperature because caffeine has a high specific heat capacity. Again, this sounds like an appealing answer. In a different context, this might actually be a correct answer. Materials that have a high specific heat capacity do have a harder time having their temperatures raised. For example, if something had a specific heat capacity of 1 versus another thing that has specific heat capacity of 5, it would be much more challenging to raise the temperature of the one with the higher specific heat capacity, because it would take more energy to raise the temperature of 1 gram of the substance by 1 degree Celsius, which is the definition of specific heat capacity. So although it may make sense at first glance, remember, that doesn't really take into account the fact that we're speaking about the sublimation step in this case. So I'm going to kind of keep my eye on option B, but I'm going to see what other options are available. Option C states the energy added was used to increase the pressure inside the apparatus. Well, again, the point of the vacuum chamber here is to decrease the pressure inside the apparatus. So this is not something we want to actively try to do. Remember, it states here that the vacuum/gas lines create a near zero pressure environment. It constantly removes gas that is exposed from the system. So this option would not make sense because it's counterproductive to what we want to have happen. And the last option states the energy added was used to break caffeine's intermolecular bonds. Now this is an interesting option. I talked a lot about changes in phase, going from solid to liquid, liquid to gas. What actually happens on the chemical level when there's a change in phase? Well, in order for there to be a change in phase, intermolecular bonds need to be broken, and then they need to be reformed in a different way. For example, when you have a solid compound, I'm just going to use a random element X. When you have a solid compound, there's a matrix that's formed in which all the molecules are very, very tightly and neatly packed with each other. But when we have to convert the solid to a gas, we need these molecules to move away from each other. So we actually have to put in energy. We have to put in energy to break these intermolecular bonds so that atoms can move further and further apart. And then the change in state could occur. So this option seems really likely because it does explain the specific sublimation step. It takes into account the changes in state, and it explains why there's no change in temperature during this point in time. And perfect. So this was a pretty tricky one because it really required you to kind of understand the process that was going on here. And if that's really not your wheelhouse, a question like this can become difficult. But remember, you have to try and isolate what information you think is relevant versus what isn't. So like I mentioned at the beginning, this whole paragraph didn't really help us with anything. when you have diagrams, you should always kind of focus on those because you will see some kind of question associated with them. And especially if you see them kind of outlining a process, you should actively be trying to think about how this process works and why it makes sense. So how does extraction occur, and how does that kind of feed into the next step, and what do we essentially get out of this sublimation purification step? So always try to kind of keep track of the steps that are occurring and how they correlate with one another. So I hope that helped. If you guys want to see more passages like this, just let me know, and good luck.